A capacitor is a device that stores electric potential energy. See, whenever we talk of potential energy, what comes to your mind is a device. Say you think of a ball thrown at a height, or a compressed spring, or a bow and arrow, because all these can store potential energy, and you know that once energy is stored in them, then that energy can be used to do some work. For instance, this arrow can hit a target, this spring can throw off a mass. When the ball comes down, it can hit an object which is placed over here. So in each of these cases, we are storing potential energy and then later on retrieving that energy back, which means we are able to store the energy and use it later on. A capacitor is an extremely useful device because in a capacitor we can store energy in its electric field. Say we have a capacitor and we connect this to a battery. Now one plate gets positively charged and the other is negatively charged, and then we just disconnect the capacitor. So the plates are going to hold the charge, so you have an electric field between the plates, and associated with this electric field you have an electric potential energy. Next, if you connect this capacitor to a resistor, the current will flow. The plates of the capacitor will get discharged and you have a flow of current. This is useful. Suppose you have a battery operated flash system in your camera. So first you charge the capacitor with the battery, and then when you want a flash, then you discharge the capacitor. So you get a quick sharp flow of current which produces the flash. Now let's take a look at what is a capacitor. See, a capacitor is two isolated conductors of any shape that are electrically insulated from each other and from their surroundings. So if you have two conductors, say, that carry a charge Q and minus Q, then you have an electric field present between these two conductors, and this system forms a capacitor. Now what we will typically look at will be a parallel plate capacitor, in which case you have two plates which are parallelly placed with respect to each other. So this is a typical arrangement of a capacitor in which one plate carries a charge of plus Q and the other is negative Q, and this is a parallel plate capacitor. Now the net charge on the capacitor is 0 because you have positive charge and an equal amount of negative charge. See, if you are charging a capacitor by connecting it to the battery, then at the positive terminal of the battery you have electrons which move from this plate to the positive terminal. So this plate has a deficit of electrons, so it has a positive charge, and at the other plate you have electrons which are moving from the battery to this plate, so this plate acquires a negative charge. It is not that the net charge on the capacitor is Q. That is not correct. The net charge on the capacitor is 0. Now the charge on the capacitor is Q and there is a potential difference V between the two plates of the capacitor. Each of the plates of the capacitor is an equipotential surface, which means the potential is the same everywhere, and the difference in potential between the two plates of the capacitor is V. Now the charge on the capacitor is Q and the potential difference is V. So Q is proportional to V, and removing the proportionality we can put a constant and write this as Q is equal to C times V. C is the capacitance of this capacitor. But a very important point is C, which is equal to Q by V, does not depend on Q and V. C depends on the geometry of the plates, the area of the plates, the distance between the plates, the medium between the plates, whether it is air, say plastic, mica. So C depends on the geometry. C does not depend on Q and V. Now the capacitance is a measure of how much charge must be put on the plates to produce a certain potential difference between them. If the capacitance is higher, that means more Q is required for a particular potential difference. Now the SI unit for capacitance is farad, and 1 farad is equal to 1 coulomb per volt. But farad is an extremely large unit. So generally you will find the capacitances mentioned in microfarad or picofarad. Microfarad is 10 to the power minus 6 and pico is 10 to the power minus 12 farad. Now what we are going to do next is we are going to calculate the expression for the capacitance of a parallel plate capacitor. Now we are going to find the capacitance for a parallel plate capacitor, and actually to see whether it is a parallel plate capacitor or a spherical capacitor, cylindrical capacitor, you can follow the same sequence of steps. But here we are going to look at a parallel plate capacitor. The first step is we'll assume a charge Q on the plates. So say these are the two plates of the capacitor. So we'll assume that each of these plates have a charge Q. Now one of the plates carries a charge Q and the other has a charge of negative Q. We need to find the value of the electric field between the plates, and for this we'll use Gauss's law. So we'll take a Gaussian surface, which is a closed surface like this. Actually this Gaussian surface is fully enclosing this plate. The Gaussian surface is in the form of a cuboid. So you have this cuboid over here which fully encloses this charge. Now we know that Gauss's law states that integral E dot ds is equal to 1 by epsilon naught times the charge enclosed. So the electric field is E times A, which is equal to 1 by epsilon naught times the total charge Q, because we've taken a Gaussian surface that encloses the entire positive plate. So now this gives us the electric field as 1 by epsilon naught times Q over A, and you know that Q over A is the surface charge density sigma. So we can write this as sigma over epsilon naught. Now the first two steps are over and we found that the electric field is sigma by epsilon naught. The potential difference V between the plates will be E times the distance D. D is the distance between the two plates. And then finally we put this into the expression for the capacitance. So we have Q, and in place of V we have E times D, and we found E as sigma over epsilon naught times D, and the total charge Q can again be written as sigma times A. So this is sigma over epsilon naught times D, and the sigma gets cancelled out and we are left with epsilon naught times A over D. So you can see that the capacitance depends on the area of the plates, the distance between the plates, and the medium in between the plates. In this case, if we've assumed that it is air, then epsilon naught is the permittivity of free space or air, which is almost the same. Two isolated conductors of any shape which are electrically insulated from each other and from their surroundings form a capacitor. When charged, the two conductors have equal but opposite charge. The net charge on the capacitor is 0. The charge on the plates of the capacitor is Q and the potential difference is V, and Q is proportional to V. So Q is equal to C times V. The capacitance C depends on the geometry of the plates and it does not depend on the value of Q and V. The capacitance is a measure of how much charge must be put on the plates to produce a certain potential difference between them. The SI unit for capacitance is farad, and 1 farad is 1 coulomb per volt, and the capacitance of a parallel plate capacitor is given by epsilon naught A over D.